All right, so we are now recording. If you're going to say bad things, save it for when the recorder is turned off. I'm opening up the chat window. I'll be sharing my screen shortly. Okay, so on Tuesday, be prepared to report by team, not by individual, on the status of your project, how far you've gotten, show us what you've done. It's pretty low key, so don't get all worried about it. I'm aware that you have other classes and you have other work in those classes for professors that are somewhat less flexible than I am. And if you are actual real freshmen, you're gonna learn what less flexible is over the next few years. I can rest assured that this is not an inflexible class. One of these days I'm gonna learn how to get rid of Outlook, so I can't turn it off. Okay, so I'm about to share my screen. Good morning, everyone, and here is my screen. And first, let me get this thing out of the way. No, come on, bad word. I usually don't go to the right corner, so hopefully that will work. All right, I can turn off my calendar. And what do we have there? I will get rid of that. Well, that's why I was able to maintain the connection. Huh. There we go. Okay, there's where I wanted to get to. And if you go to Blackboard, I'll be talking from this. There's nothing in this particular book of consequence for today, other than it's a notes to myself. So ultimately today, you're going to learn about support vector machines, decision trees, and random forests. First, I want to show you a couple of articles. So if I had shown this on the first day of class, my guess is that as I scroll down, you would have very little insight into what's going on. But now let's see what we've accomplished over 3 months. Those are words that I'm scrolling through because nobody reads. But this is a paper on a particular type of data model. And I am going to speculate that when I show you the model, it's going to look strangely familiar. So look at equation 3 on the screen. Everyone see it? It says y sub I equals boldface cap x sub I times some funny looking character plus some other stuff. Based on what you've had in this class, what kind of data model is that?
Look like a linear regression.
That's a very good guess. It's not exactly, but that was what I was trying to prompt from you all. So that's a multivariate linear regression type model. We have what we're trying to predict our response. We have a whole different set of observations, and we have CapX, which is called a design matrix. In our linear models, our CapX matrix usually was a column of ones and then a column of the x's. So x sub 1, x sub 2, and so on. In this case, it has more dimensions than just the rows. There's also some secondary and tertiary dimensions. This theta is the unknown parameter matrix that we're trying to find values for. Okay, good. And so this should look quite familiar, although it's a different software tool than what we've used. Using the metrics that Farang taught you in lab, what can you say from this report on the generalized additive model with respect to whatever the underlying database is? So there's no picture yet. That's coming up on the guitar shortly. But does this appear to be a pretty good model or a pretty crappy model? And whatever answer you make, justify it.
I'm thinking pretty good.
Okay.
The deviance explained 94.9%.
Good. So you are actually able to interpret output from a statistical data model that you've never seen before and make an assessment or a judgment on the quality of that model. And that was what I was after. So you looked at the R squared, and there's a few other metrics here, and we're able to make an interpretation. Now let's look at this picture. This is the result of that. Actually, that came out pretty dang good. So that particular model is different than what we've studied in this class because we're also dealing with space on the surface of the Earth as well as data space. So we have these contour lines, but you'll notice there are red and kind of greenish blue contour lines that are oriented around the solid black contour lines. So what do those red and blue dashed contour lines represent in context of what we have had in this class?
Is that our range?
Close. You're very close.
I mean like the confidence interval sort of thing.
Good. Yeah, it's prediction intervals. So what it's trying to convey visually is that that solid contour line is where the computer model thinks the particular this is a discharge parameter, where the parameter is supposed to be in space, in XY space or latitude longitude space, but there is a lower and upper single standard error variation represented by the dashed lines. So it suggests that there's 68% chance that the solid black line falls somewhere between the dash blue and the dash red line for each category or each location. So that's identical to the prediction intervals that Farang taught you in lab, although in higher spatial dimensions than we ever talk about. And now let's look at our residual plots. These are base 10 residuals, and what this plot is really showing us is conveying that most of our residuals are between -0.5 and +0.5 base 10. So that's basically the difference between half and twofold. So when you go into ordinary space. So that's basically a third of a log cycle is being represented by the 18,000 some odd data. And then the remainder of the paper talks about a velocity model. And let's take a look at equation number 7. What kind of data model does that appear to you to be? A bit of a trick question, but anyone can make a guess based on what we actually talked about in class.
Is it a log function or
Yeah.
multi-log function?
You're close. What are the predictor variables implied by that equation? The letters of the alphabet.
Q, B, and P.
Yeah, and actually omega and then longitude, latitude. Good, good. What's getting predicted?
Velocity.
Actually, the fifth root of velocity. So this is a weird way of dealing with nonlinearities in modeling space by taking logarithms of a couple of the predictors. That kind of straightens out things, and then using a weird fifth root. Certainly, we didn't start out the paper by thinking, well, the fifth root of velocity is going to be our best choice. So there's clearly been repeated fits of different data models. And this data model was selected over all the other ones that we tried. Without actually having it in front of you, how would you characterize that we made that selection? Because you all know how to do this. You just don't know that you do.
Can you ask that question again?
Say it again.
Can you ask that question again?
How did we choose this particular data model over whatever other ones we tried?
You mean other than visually?
Yes, other than visually.
MSC and RMSC, there's just a
Good.
few.
Correct. That's correct. We did several different data models, and the one that had the most explainable residual error was the one that was kept. And in this case, we don't get as good behavior as we got on discharge. So the best explainable residual error that we got was 67%, which in a lot of your statistics classes would be considered pretty crummy. But for this particular work, that was about the best we could do. And keeping in mind, F9 and F10 are functions. They're not the usual way of a data model. And again, the same visual representation of results. And the visual error is the residual is contained as this dot right in the middle of log space. And then finally, this is actually very relevant to your projects. So once we've done all that, the goal of that wasn't to make these cool pictures, except to get the paper published. The goal was to produce an equation like equation 8, which now allows a designer to estimate the log of discharge based on latitude, longitude, mean annual precipitation, and the omega function, which comes from a map. And similarly, we can also estimate mean velocity, either directly with the GAM model or with prior knowledge of what the hydraulics is. So the whole point of all the data modeling, the whole point of this class is to get to some equation like that. Now the 450, the 100, the minus 0.106, those change depending on where you are in this case in the state of Texas. And then there's some additional discussion, and then so forth. So I maintain that in this class, you now could effectively read a paper like this. Okay, let's go take a look at a different paper, which is actually kind of segueing into today's class. Same author, and now we're looking at a different type of modeling. But as we zoom in, Does that look familiar? Equation 1? That's a yes or no question with only one correct answer. So
Yes.
yeah, it's just another model. We have this beta 0 without even knowing what it's modeling. I have maintained that you all can read that. Beta 0 is some fundamental constant. Think of it as an intercept. The bold capital X is a design matrix. This funny looking thing is the other unknown parameters. In our case, are beta 1, beta 2, and so forth. We have some functions that are themselves the result of different predictors. And finally, we have an error term. And then a variety of methods are used to find values for that function. So a support vector machine, you're going to learn a little bit about that from Farang, who's I think is back with us now, is a type of machine learning tool where complex linear combinations, that's what equation 1 is, a complex linear combination of predictors, which are called the support vectors, and the varying weights are used to define a hyperplane through the data. Now, Farang's presentation, this is his area of expertise, so that's why he's going to take over shortly, are used to pass planes that separate different parts of the multidimensional space. That's what a support vector machine is doing. And I drew the idea of a support a few weeks ago. And when we get done, we might have a more complicated thing that looks like this, but take a look at this equation number 6. Does that look at all like anything you've seen before? Also, there's only one correct answer and it begins with the letter Y. Yeah, that's just a linear model where it's saying that Z, whatever Z is equal to beta 0 plus beta 1 times whatever U1 is plus beta 2 times U2 all the way out to beta P UP. So again, everything you've been dealing with is real and relevant. And also, again, we're dealing with a spatial behavior. So the red lines and blue dots, or in this case, red lines, blue lines, and black dots are not original to Farang and myself. Other people use that. And we can have a lot of fun with attempting spatial representation. And in this case, one might look at that picture and say, whatever this is, it's really good because there's not the upper and lower standard error estimates are kind of really tight around the predictions, the solid black lines. But it depends on what the actual units of these easting and northing distances are. So I'm thinking this is encompassing something the size of the state of Texas. So this represents nearly 1,000 miles in the horizontal and 1,000 miles in the vertical. So those little teeny variations are probably pretty substantial in real space. And then, like we've shown you, anything you can plot, you plot the crap out of it. And this is what you really want to have happen, is the generalized additive model and the support vector machine model. What this plot is showing us, and does there appear to be a correlation between support vector and generalized additive model? Let me just ask you a question.
Yes.
Yeah,
Yes.
Yes.
yeah, I'd say there's a pretty dang good correlation. And this plot is used to justify the use of a support vector machine. So generalized additive models are pretty well accepted in the industry. And support vector machines are considered weird, so nobody trusts them. But this plot is the author's attempt to argue that the support vector machine and the GAM model are pretty much producing similar results, but we want to use a support vector machine because we can go into no brain required type of analysis. And then the rest of this has some other description. How about this plot? What does that look like to y'all?
Logistic.
Logistic.
regression.
Very good. Okay, so you guys learned something. I'm extremely happy for you. Unlike a true logistic, the horizontal axis is actually a probability and the vertical axis is your 0, 1. So actually they have a lot of similarity. And then here's another one, same kind of thing. So if we're sitting there at the door, who do we kill?
Blue.
Blue. So when do we start killing? When are they blue enough to kill?
I'm thinking
45, 50.
Like here, where the cursor is?
Nah, that's too late.
That's
40, 45. Everything after that, suspicious.
So you want to kill everything after these two. Do these two get in or do they get killed?
Nah, they gotta go.
They got to go. Very good. Okay, and then Caden is drawing all over my. And then here is the actual real world manifestation of what these models are trying to display. So I will leave that. And what else did I have for myself? I'm actually, the database that at least started that whole thing is not very big. There's only 87,000 lines in it. And actually in the world of database, that's considered a pretty small database. But if we look at it, I dare say that you all would know how to read that and process it. How many columns are represented in the database?
14, I think.
Okay, I'll buy that. Do any of the records have common items, meaning the same thing?
Yeah, I see a 0.01 and a 48636.71 and a 0.00933058.
You see a lot of these. Those columns for station number 722, 7500, all of the same information. So clearly that is something that is specific to that record. And then the varying portions are out here. So very good. That's what you've learned this semester, believe it or not. And you would read that in pandas and then start renaming column names and go to town with it. Okay, so I just wanted to do that mostly to make the case that all the silly stuff we've had you do has real world application. You've just seen 2 journal publications. I'm a co-author on one of them, and this fellow Asquith happens to be one of my former PhD students. So all this stuff is real world. At this moment in time, you would expectedly be kind of hard pressed to make sense of that, but keep these skills up as you continue on with your career. Okay, Farang, are you ready to go through?
Yes, sir.
Okay, let me tell everybody where it is. And if you go into laboratory collection, today is laboratory 25, and the actual title of the lab is A Tale of Machines, Trees, and Forests. I'm now going to turn over control to Farang.
Thank you very much. So do they know everything they need to know about Tuesday?
Probably not. Tuesday, we want them to make a short presentation by teams on their project. That's what we discussed, right?
Yes.
So
So it will be more of a progress report. You don't have to have your final product necessarily. Just you will come out there, tell us what you've done so far, what is your plan for the next steps, and how you are going to tackle it.
Is there any team that is willing to go first?
We
Simon,
can go based on, okay, Wally.
We'll go second.
go second.
I wanted to suggest we can go on our alphabetical order.
Yeah, this would be a good time if you're a team to volunteer. So you always want to go first on something like this, or last, but never in between.
I think someone in the chat said they want to go first.
No, Harper's fired. Okay, Caden's team said they will go first. So you guys will be first up on Tuesday. We'll do like a 5-minute introduction, let everybody get here, and then we will hand off control of the screen to y'all for a few minutes. If you are going to get together and prepare, we wanted to keep it, try to give yourself a 5-minute window. 5 minutes goes by amazingly fast when you're doing a presentation. You will be quite surprised at how quickly that 5 minutes goes away. All right, Farang, let's see, the recorder is on. I'm gonna mute myself. I will be around, but I'm gonna be messing with some other stuff at the house. So I will turn off my video and mute myself.
So let me put everything together. We are working on lab 25, a tale of machines, trees, and forests. So I want to give you an official welcome to your last lab of this course.
I need to interrupt real quick. Is there a
Sure.
database that goes with that lab?
I don't think so.
Okay.
We are going to use the Iris dataset, and they have it. Yep.
All right.
So let us see what we have today. We're going to begin with support vector machines. So based on what you just heard from Dr. Cleveland, what can you tell me about support vector machines? What are they? What do they do? Why do we need them?
They're kind of like the goodness of fit models that we had before, where we would judge whether the model was good enough. So with support vectors, basically be judging the these new models that we've been learning since then.
Kinda. Support vector machines are actual models. So we had linear regression models, we had logistic regression models, we had naive Bayes classifiers. These are all different models or algorithms, if you may. And support vector machine is just another one. And in this algorithm, we plot each data item as a point in a n-dimensional space, where n is the number of features you have. So if you have 2 inputs, we can plot it on a 2-dimensional graph. If you have 3 inputs, we can plot it on a 3-dimensional graph. But if you have more than 3, it is visually impossible for us to present it. Now, in an example like this, we are looking at a problem that has how many input features?
2.
2, exactly. We are plotting one of them on the x-axis, the other one on the y-axis, and we get a bunch of points. What do you think the colors are telling us?
Which class the points belong to?
Exactly. So they are basically acting as labels. Aaron, that is also correct. So we have 2 classes in this example, class green and class red. And this line is a front that is separating class green and class red. Would you say that it's doing a good job?
Mm-hmm.
Yes, I would say so. Now, the general idea of support vector machines is to come up with the hyperplane that differentiates the classes the best. Question: what is a hyperplane? Have you worked with it before in your other classes?
Upper dimensional planes, more than 2 dimensions.
Any other ideas? The middle line. In this case, this middle line can be considered a hyperplane, but it has a broader definition to it. And I have that definition here for you. So in geometry, a hyperplane is a subspace whose dimension is one less than that of its ambient space. So if you are in the 3-dimensional space, your hyperplane is going to be a 2-dimensional plane. What if you are in a 2-dimensional space? What will your hyperplane look like?
A 1-dimensional line.
It will be a 1-dimensional line. What if you are looking at a 1-dimensional line? What will your hyperplane be?
A dot
Exactly.
or point.
Exactly. Thank you. So in this example, in the first one, we are looking at a 2-dimensional space, and this blue line is the hyperplane that is separating the two classes. In this other one, we are looking at a we are looking at a 3-dimensional space, and this blue hyperplane, which in this case is a plane, is a 2-dimensional plane, is being used to separate the red squares and the green circles. Do we have any questions about the hyperplanes and how they work? Okay. Now,
You said the red dot separating.
come again.
I was confused about so the blue line separates the red and green dot.
So depending on your space, your hyperplane is going to have one less dimension. So if you are in the 3-dimensional space like this one, your hyperplane is going to have 2 dimensions and it's going to look like a plane. But if your space has 2 dimensions like this one, then your hyperplane is going to look like a line which has 1 dimension. You got it? Okay. So support vectors are simply the coordinates of individual observations. The SVM classifier is a frontier which best segregates the two classes, or it's the best hyperplane, or it's the best line. And in a case like these, we have these points or these coordinates which are support vectors, and then we come up with a line or a hyperplane that separates them the best. Now, how does it work? Here I have a game to play, so be ready to use your chat box or your microphones. Identify the right hyperplane. In this case, between A, B, and C, which one do you think is a better hyperplane? I'm getting some B's in the chat box. Do I have anyone who wants to pick A or C? Brandon says A. What do you mean by Q, John? Okay, Wally, unmute your mic and elaborate on your answer.
Well, if you add the areas of A and B together. You cover all your spots, so you can't be wrong.
So one line would be A. If we take A and say everything below A is stars, everything above A is circles, we are going to have 3 misclassifications, correct?
Yes.
So A is not a very good hyperplane for separating the stars and circles. But if you look at B, you see that if we take B and say everything to the right is going to be circles, everything to the left is going to be stars. Do we have any misclassifications in that case?
No.
So B is the best hyperplane in this example. Deal?
Deal.
Okay, now, remember a thumb rule to identify the right hyperplane. Select the hyperplane which segregation of class is better. In this scenario, hyperplane B has excellently performed this job. Moving to scenario 2, between A, B, and C, which one is the best hyperplane?
C.
I have C, 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 and that's Julissa. Keep on casting your votes in the chat box. So far, all I have is C. Come on, wake up. There you go. Okay, so Travis, as the representative of those who voted C, why do you think C is a better hyperplane?
It took me a while to find the button. I think it's because it's very much equidistant from the nearest red circle and the nearest star. So it has very little bias between the two.
So now you're looking at distance. I thought we were looking at whether we can use these lines to separate the classes without any misclassification. So if I take B, if I take C, or if I take A as my separating line, I will have no misclassification. Everything to the right is going to be circles, everything to the left is going to be stars. Why are you looking at distance?
No, I found the button again. Trying to think of how to explain it. It has a better.
Quick hint, I'm just being the devil here. You are on the right track. So
Okay. Because there's a greater margin of, not margin of error.
Go on. You actually, that was bullseye. Yes, you touched on the exact right term. So maximizing the distance between nearest data point in either class and the hyperplane will help us to decide the right hyperplane in cases like this. This distance is called margin. Let's look at this snapshot. So if I pick this line as my dividing hyperplane, the distance between this line and the closest point of class green is my margin on this side. And the distance between this line and the closest point of the red class is going to be my margin on this side. If we look back at our example, line C is the one that gives us the largest margin, hence more confidence for our classification. Do we all agree on this?
What you're saying is that what makes C a better hyperline is that it has more room for error.
Exactly.
As a margin, as a hyperline, because let's say if A was it and then we have a dot let's say A cut through, that wouldn't be good. But we see we have
Exactly.
confidence.
Exactly. You are absolutely right. So far in these scenarios, we have learned that we are looking at misclassification, or basically avoiding misclassification, and maintaining the largest possible margin that we can. Correct?
Yes.
Okay. Now, scenario 3, identify the right hyperplane. In this example, between A and B, which one do you think is a better hyperplane to choose? Before you start casting your votes, okay, you're already doing it, but I'm going to give you this explanation. A is the hyperplane that will give you a classification with no errors. All the stars are on one side, all the circles on the other side. But B is the hyperplane that will give you the largest margins. So now cast your votes, A or B. So I have 3 A's, I have one kind of B, another B. Okay. It's interesting,
B.
it's getting more balanced. Okay. Keep on. This is the most interesting round so far. Cast your votes, make your bets. Come on, guys, this is the last lab. Be more active. So, Jalissa and Caden, kind of B is still B, right?
Yeah, I'll stick B.
Okay. So I want one volunteer to speak for the team that chose B. Who wants to be that person?
I can do it.
Okay. Why do you think B is better?
Well, it kind of just depends on what you find to be more important in your data. Do you want it to correctly classify every single one of your predetermined variables, or do you want it to be more good at predicting general trends? And I think there's a chance that that one star on the side could be our favorite word, outlier, and that it could perhaps just be a discrepancy in the data, in which case it wouldn't actually be good for predicting future data. So that's why I picked B.
Okay. I want a volunteer to speak for team A. Or was Caden's speech so influential that all of you are converting to team B? Come on, no one wants to defend their opinion on A?
So going with A, we haven't done the analysis on this to determine if that's an outlier. So looking at what we have right now, A perfectly classifies everything, is the most perfect model we could ever have.
So you are telling me that avoiding misclassification has a higher priority than maintaining the margin?
Yes.
Okay. And while, okay, let me tell you, since this is the last session, I can be frank and tell you, so far I'm really proud of both of your justifications. And for some reason, people who came up with the theory of support vector machines thought like Harper. So in their mindset, avoiding misclassification has a higher priority. So even though B has the highest margin, because it ends up with a misclassification, A is chosen in this algorithm.
So basically, even though we're closer to the edge, we rather the edge is still has no error.
Exactly. So you are looking at two items: avoiding misclassification, maintaining the largest margin. But the first one is more important. So if you have to go with a trade-off, you have to pick one or the other. You prefer to stick with avoiding errors. Now, scenario 4, identify the right hyperplane. So in this case, you have to actually tell me where you would draw that line.
It's got to be a straight line, right?
Yes. I am unable to segregate the two classes using a straight line, as one of the star lies in the territory of other circles as an outlier. So Caden comes in.
Probably about there.
Okay, that is Caden's suggested hyperplane. Did you remove it? Let it be there.
Sorry, I didn't think you wanted it there.
Okay, if I have someone else who wants to step into my screen and draw a hyperplane, you're welcome to.
So
Come on, let's
I
see
don't know how to
some
do that,
lines.
but can I say that the hyperline would be the same one Caden drawn, but in the opposite direction?
The same, okay. So yours with Caden's will make an X.
Yeah.
Okay. Any other ideas? Thank you, Caden. So you are noticing that in all of your suggestions, we are having a misclassification, right?
Yep.
And you don't care?
This is going to keep me up at night. I care for it.
So this is exactly what, okay, Sean comes in with another one. Okay. But the main difference between your hyperplanes is their margin. Because in terms of errors, they are all doing the same thing. You are having one case of misclassification with your star being in the side of your circles. So let me see if I can clean this screen. Okay, thank you, Kate. The SVM algorithm has a feature to ignore outliers and find the hyperplane that has the maximum margin. So it will basically do what you did. And the hyperplane chosen will be something like this. Because of this feature, we actually say that SVM is robust to outliers. Now, is it a good thing? Is it a bad thing? Really depends on what you want to do. But that's just one of the characteristics of this algorithm. Now, scenario 5. In the scenario below, you are asked to draw the best hyperplane to separate circles and stars. Go on. If you want, you can draw your suggested hyperplanes, or you can describe them in the chat box or through your microphones. Wally, what do you mean? Can I draw a box or a circle? Well, we are trying to find hyperplanes So a hyperplane in this case is going to be a line. Who did that magenta? Is that you, Caden?
That's the best I can do, I think.
Okay. Will you be offended if I tell you that it's a terrible hyperplane?
Yep, I will be.
So the only way for this to have a hyperplane is for the image to be 3D with the stars in the back. Brandon, explain more. Okay, I am having.
How are you drawing on this? Like, how do I draw?
I think you can use your annotate feature.
At the top of the screen, there's a button that says View Options. Click that, annotate.
Come on, guys, share your ideas, share your hyperplanes, and tell me what you think about this problem. Okay. Brandon, I really like how you think, honestly. And in a few moments, you will know why. So thank you very much for sharing your hyperplanes. But I think you all would agree that none of them are ideal. So if we want to go with any of them, there will be some severe misclassifications of either classes. So annotate, clear all drawings. Okay. SVM can solve this problem easily. It solves this problem by introducing additional features. Here, we will add a new feature z, which is equal to x to the power of 2 plus y to the power of 2. Now, if we plot x and z on our axis, x on the horizontal, z on the vertical, we will have this. This is beautiful, isn't it? Now you can easily separate them. So basically, by changing y to z, we have made this linearly unseparable situation to a linearly separable situation, which we like. And the above plot points to consider are all values for z would be positive. Why? Because z is the squared sum of both x and y. In the original plot, red circles appear close to the origin of x and y axis, so they are in the inner circle. Hence, they will have lower z values and will fall closer and below the blue stars. In the SVM classifier, it is easy to have a linear hyperplane between these two classes. But the question would be, should we need to add this feature manually every time we are dealing with a classification problem? And thanks God, the answer is no. The SVM algorithm has a technique called the kernel trick. The SVM kernel, this is important. The SVM kernel is a function that takes low-dimensional input space and transforms it to a higher dimensional space. As a very wise man in the room said, if you could look at this two-dimensional plot in 3 dimensions, it would be easier for you to do the separation. So the SVM kernel is a function that takes low-dimensional input space and transforms it into a higher dimensional space. It is mostly useful in nonlinear separation problems. Simply put, it does some extremely complex data transformations and then finds out the process to separate the data based on the labels or outputs that you've defined. Now, if you convert this straight line back to your XY scales, you will see that your hyperplane shows up as a circle. Wally, does this sound similar to what you were suggesting?
Yes.
So this line, this straight line, one-dimensional hyperplane that we had in the ZX space, will look like a circle in the YX space. You want to see something cooler? Check this out. In the two-dimensional space, we had variable 1, variable 2, x or y, and we had a bunch of points. It is very hard to come up with a straight line to separate them. So we use the kernel function to take this two-dimensional representation to a 3D dimensional representation. And by this, it is very easy for us to cut the purple circles and the green circles. You see this as green, right?
Yes.
Okay. And if you convert this back again to the same two-dimensional space, you will see this circle. This is a very, very important and clear picture. I want you to have a look at it for a few seconds and let me know if there is anything about it that you do not understand.
So, what are we doing with this?
Come again?
What are we doing with this? Sorry, I left my computer for a second.
So, this is your original problem. You have 2 variables, 2 inputs, and you want to come up with a hyperplane to separate purple points and green points. Okay?
Yes.
Can you draw a line to separate these with minimum misclassification?
No.
No. So no good linear decision boundary is seen here. If we apply the kernel trick of the support vector machines, we can take this from two-dimensional space to three-dimensional space. And we will have something like this. The circle, the purple circles in the middle, the green circles surrounding them. Now, in a three-dimensional space, how will my hyperplane look?
Plane.
A plane. This pink plane is going to be my linear decision hyperplane. Can I move it up or down so that I can separate purples from greens?
Yes.
So if I do that, my problem is solved because my goal was to come up with a hyperplane to separate purples and greens. And in the three-dimensional space that I have thanks to my kernel, I can do that. Now, if you start looking at this three-dimensional hyperplane from the top again, how would you see this decision boundary?
Circle.
A circle, this circle. So it's just a matter of perspective. And the kernel trick allows you to change your perspective and look at it from three-dimensional view. Are we clear on this?
Yes.
I want you to realize that we left all these for your demo because we didn't want you to worry about applying it on an exam or it affecting your grade. But these are extremely important, extremely useful concepts in real world. And when you are going to join the workforce, these are the things that are going to give you an edge. You will be the ladies and the guys who know what a support vector machine is and how it is working and why it is beneficial. Any questions? Okay. There are different kernels that we can use. Linear, sigmoid, polynomial, radial basis, and so on. Depending on the kind of problem that you're working with, you may use one of them, and you may prefer one of them more than the others. So this is a linear kernel. This is a second polynomial kernel. This is a third polynomial kernel. A radial basis, which gives you that circular hyperplanes, and then the sigmoid. So depending on the kind of problem that you have, they will have application for you or not. So if you have one class separated on both sides, you may use a sigmoid. If you are dealing with rather distinct decision boundaries that are just not linear, a third polynomial may do the trick for you. So the difference between the first one and the third one is that this decision boundary is more clear in the first one. Yes, very much. So let's see how to implement SVM in Python. We are going to reuse our iris plants classification dataset. You remember this problem?
Yes.
We have three kinds of plants. We are trying to classify them based on a bunch of input features. Now, if you notice, in my first code cell, there are two things that are a little different from what we had before. First, I am importing data sets from Skylern because there is a version of this iris database in that package that you can use. So you can either use the CSV file that we have given you, I think 2 weeks ago, or you can use this. And then I'm importing the SVM function to apply support vector machines. Now, I'm going to load iris data from my package, and I'm going to only use 2 inputs. Why? Why am I using only 2 inputs?
Because that's the dimensions we want.
Yes, because of illustration purposes. I want to be able to show plots, but you can use all 4. And then my target is going to be my Y, which will be the type of plant. Now, very similar to other predictive models that we've dealt with, we are going to set up our SVM. Here, I can decide on the kernel. I will go with a linear kernel, and then I'm going to fit that on my X and Y. I will create a mesh and prepare a plot like this. Can you tell me what you see in this plot?
2 classes.
Do you see 2?
Actually, 3.
3, yes. It may not be the most distinct set of colors, but yes, 3 classes. What do you see on the x-axis? Thank you, Harper. What do you see on the y-axis?
With
And if I ask you, separating which one of the classes based on sepal length and width is easier, what would you say?
the blue one,
Why?
because it's far away.
Because you see a quite well-defined cluster of blue points on this part of the plot. What about the other classes? Do you think they are easy to separate?
No,
Why not?
because they're intertwined with one another.
Yeah, because they are kind of mixed. So you would say it looks kind of noisy. Now, if I apply the results of my support vector machine on this is what I will get. So my support vector machine says anything on this corner is going to be class blue, which kind of makes sense. And you see that we have no misclassification there. And then it is going to give me this and says everything on this part is going to be brown, everything on this side is going to be red. But do you identify misclassifications?
Yes.
Plenty of them, actually, especially in this area. We are seeing several misclassification cases. Now, what do you think will happen if I change my kernel from linear to radial basis? Do you think it is going to make it better?
It's going to start putting circles around the points. It's going to make it better. It's not going to be perfect.
Or at least you can say that your decision boundaries are going to be more curvy because we're using the radial basis. Now, if I apply that, this is what I will get. Would you say this is better than this? I have 1 no. Come on, answer the question.
Can you show it again? Both of them.
This and this.
Basically the same thing.
So even though the form of our decision boundaries are different, we're still suffering from misclassification in the noisy area of our data set, correct? So it is very important for you to realize that changing kernels may not always be the miracle that you're looking for. In some cases, it is going to be very helpful. In some other cases, your data set is just too noisy and it cannot be handled by your support vector machine. There are 2 parameters with your kernels that will kind of have an impact on your classification results. The first one is gamma, kernel coefficient for radial basis function, polynomial, and sigmoid. The higher the value of gamma, the more sample specific your decision boundaries will become. So this is gamma 0. This is gamma 100. Do you see what is happening here? It is basically only look at each point to make the decision boundary. And in this case, we would say that we are suffering from severe overfitting. Our model is learning the noise and cannot separate that from actual relationships. So selecting the right value for gamma is important. Now, the other parameter is the penalty parameter, or C of the error term. It also controls the trade-off between smooth decision boundaries and classifying the training points correctly. So you will see the impact of C being changed from 1 to 100 to 1000. And you see that when you go with a very high penalty parameter, you will end up with weird decision areas like this that doesn't make any sense. So gamma and C are parameters that you may want to keep a close eye on. Now, let us say that we want to use support vector machines to solve the exact same problem that we were dealing with before. How many inputs were we using in last sessions?
We're using multiple inputs.
We were using all of them, all 4 inputs, and we will trying to predict the plant type. So I'm selecting all my inputs. I'm defining my target as the plant type. I'm going with a 75%, 25% separation of data set for training and testing. And I'm going to apply my support vector machine on my training data. And then I will apply the trained model on my testing data. And then I can go on and evaluate my model. So what do you think about this confusion matrix? It is pretty good, right?
What, I have a question. What does the 14, 12, and 11 represent? Like, what is it showing?
Okay, so the first number is telling you that you had 14 plants belonging to class 1, and your model actually captured them correctly. So in identifying the first type of plant, you have no misclassification, 14 out of 14. How do I know that there is no misclassification? These zeros. Now, what about the second type? Abby, what do you think about the performance of this model in detecting the second type of plants?
Let's see. Oh, can you hear me? Okay.
Yes.
So we see that I was able to predict 12 actual values correctly, but we have 1 misclassification.
Since when I'm running my confusion matrix, I'm using ytest first and pred second. The values I have in the rows are the actual values, and the values that I have in columns are the predicted values. So I had 13 observed plants in the second class, and out of those, 12 were correctly classified by my model. Thank you, Abby. And the third type, who wants to talk about the third type?
So the third type means that you had 11 were correctly predicted.
Exactly. I had 11 cases. All of them were predicted and classified correctly. So except for that one case, this is a very good classifier. Does Harper approve? Okay. So you can look at precision recall FS score, and you see that it is doing pretty good. So I want at least one of you to go back and compare the values that we are getting from support vector machines with logistic regression and naive Bayes classifier, and tell me which one is winning. Meanwhile, I'm going to talk about the pros and cons associated with support vector machines. It works really well with a clear margin of separation. It is effective in high dimensional spaces. It is effective in cases where the number of dimensions is greater than the number of samples. it uses a subset of training points in the decision function, so it is also memory efficient, and it allows utilization of different kernel functions for the decision function, which also makes it versatile and flexible for different kinds of problems. Now, for cons, it doesn't perform well when we have large data set because the required training time is higher. And it also doesn't perform very well when the data set has more noise or target classes are overlapping, as we saw in this case. So, who did the comparison?
Wait, what? Who did the comparison?
Who did the comparison between support vector machine, logistic regression, and naive Bayes classifier?
Oh, I'm looking at it right now.
Okay, what do you see?
So we're supposed to be comparing the different kernel types?
No. We in the previous sessions we have used different classifiers on the same problem, and now that we have used it with support vector machine, I wanted some of you to go and check whether this is doing better than the other models or the same.
So,
Okay.
based on what I see, this model does a better job.
Why?
So we have the same values for the iris setosa, but then for iris versicolor, oh my god, we have a lower recall, a slightly lower recall value from the Bayes modeling thing. Let's see. Oh, damn.
But overall, would you pick support vector machines over the other two?
I would go with the support vector machines, to be honest.
Good. Thank you. So, before we go for decision trees and random forests, I am going to give you a 10-minute break or an 8-minute break. So, if you want to go have a peanut butter sandwich or anything, I will meet you back at 11:30.
I'm ordering Buffalo Wild Wings when this class is over.
I was actually thinking about something, and we might be able to go to Buffalo Wild Wings and eat together. But I need to double check this with Dr. Cleveland and see if I am legally allowed to do something like that.
We gotta do on Tuesday or Thursday though for a boneless night or buy one get one night.
Yeah, that is completely reasonable. So I will let you know next week.
That'd be so cool.
My preference would be to do this after your grades are out, because in that case, many of you wouldn't want to see my face again. But I think some of you are going to leave the town, so you may have to do it earlier.
Yeah, I have to leave.
Speaking of grades, did we ever get exam 2 graded?
Dr. Cleveland, are you there? I think he's probably not close to his computer, but that is a question for him.
Muted.
Oh,
Yeah,
hi.
Everybody failed exam 2, so don't worry about it. And
All right, that's good.
um,
It's gonna get curved then, so that's fine.
yeah, it's. I think it's been graded. I guess that's me. I haven't activated it so you can see your scores. But most of the stuff has been graded. There are some outstanding homeworks and labs that have not been scored yet. So if I think it shows you a brown circle on your score sheet if it's been submitted but not scored. So it'll all be done before we choose letters of the alphabet. Fortunately, there's only one vowel that you need to be concerned with. and then a bunch of consonants. And that's where we are on that. As for your question, can you meet them at Buffalo Wild Wings? You're certainly allowed to. The standing Texas Tech policies, you can't pay for adult beverages with your money or actually any other person's money. And your idea to meet after grades are in is sound, because then there is no appearance of influence.
I'll buy your food for an A.
So, does that answer the questions you had, Farhang?
Yes, thank you very much. And by the way, Caden, Lubbock does not have such a fancy restaurant so that you can buy your grade.
Yeah, probably not.
Yeah, even the Brazilian steakhouse isn't fancy enough to get a grade. I think they're out of
I think they closed that.
Yeah, I anything that's good is out of business. So
yeah.
So as Abby, adult beverages, in theory, we're not allowed to purchase them for y'all.
So, guys, do you know what is the last date for scores, like finalized?
I think the 7th or 11th. I'm not sure.
I think it's May 11th is
11th.
That's when I said everything is due.
So those of you who are in town on May 12th, we can we can do something on that date after all the grades are finalized.
All right.
The usual way to finesse that rule is, in the past, I don't do this much anymore because I don't get out of the house. Occasionally we would meet at a place, and amazingly, there would be cash on the floor next to somebody's foot. And so look at that. That covers everybody's costs. I wonder how that got there. Be subtle with that, but that would be what I would defend if I went before the Judiciary Committee, if it was ever called on that. It's like, no, I didn't pay for it. We just found these $50 bills on the floor. It was just amazing.
Can I get some confirmation on May 12th? I have to request off like really early. Is that what we're going to aim for?
I think so. Abby, the other ones who were interested in the idea, are you going to be available on that date?
No, I have to move out.
Oh, you must be in a dorm.
Yeah, I know.
Yeah, that's the biggest racket on the planet. Is we charge you for a year of occupancy, but you got to move out for 4.5 months of that year. It's brilliant business, but it stinks. So as soon as you can, let me turn off the record. Actually, I'll screw it up. As soon as you can get out of the dorms, it is financially a good move, because then your rent is actually paying rent. But I didn't say that because that violates some other policy, no doubt. Wally is in Mesquite. Yeah, that'd be a long drive for you, dude. I don't think you should drive to Lubbock just to have wings with us.
And for all of you who are not going to be there, I am terribly sorry, but
Jordan's in Weatherford. That's only 5 hours. Mesquite's like 7. 8 hours for wings depends on the amount of wings. Yeah, see, if you're in Mesquite, go over to Balch Springs. There's some good wing spots there. Next semester, gonna live with 3 other girls. That's gonna be one crazy apartment, Abby.
Dr. Cleveland, I live near Balch Springs. Where are those wings places at?
They're out on the interstate, the one that goes kind of north-south. I can't remember the road number right there. It's right where you move from Mesquite into Dallas proper. There's a bunch of restaurants there.
Gotcha.
Sure they're still there, but it's been a long time since I've been over those parts of Texas.
So, Caden, May 12th is a Wednesday. You said that it's better that if we go on a Tuesday or Thursday, right?
No, I just said that all right. Well, I'm looking at my hot schedules here. That's what I use to get my schedule. And I need to request off in the next 20 minutes to get May 12th off. So
that's what I wanted to confirm. If you want a Thursday, we should go on May 13th.
yeah, that May 13th would probably be better for me.
Okay. Dr. Cleveland, does that work for you as well?
What? I just walked off to get a...
Would you like to have wings with us on May 13th?
I will probably not join you, but you'll go have fun.
Okay. So, Caden, I will, you can go shoot for May 13th. And then the rest of the arrangements I'll also leave with you. So letting everyone know, and those who are interested can come in. On that day, it's going to be a very safe gathering because your grades are all finalized. You can drink if you want. You can order whatever you want. We're going to sit together, communicate like normal humans. Sorry.
We want to see the dog.
I will bring her in at the end of the session. So let us go back to the lab. Abby, that would be very nice. And Alan, yes, she just went crazy for the postman. Okay, exactly, Brent. So decision trees and random forests. Decision trees, or classification and regression tree or CART models, are extremely intuitive ways to classify or label objects. It is basically a series of yes/no questions. And you will keep asking, what is happening with my voice? You will keep asking questions until you end up with the right label. For example, let's say that you're going to use a decision tree to classify an animal that you come across while on a hike. The first question is going to be, how big is the animal? If it is less than 1 meter, we are going this way. If it is greater than 1 meter, we are going this way. Okay, if it was greater than 1 meter, does the animal have horns? If yes, we go this way. If no, we go this way. And then if yes, are the horns longer than 10 centimeters? Or if no, is the animal wearing a collar? These questions, there are a few characteristics for them. First of all, they are for binary splitting. So yes or no is usually the kind that we want. And then if these questions are designed well, they are supposed to break the number of options by approximately the half. Not exactly 50-50, because that is very hard to achieve, but approximately. The trick, of course, comes in deciding which questions to ask at each step. In machine learning implementations of decision trees, the questions generally take the form of axis-aligned splits in the data. That is, each node in the tree splits the data into 2 groups using a cutoff value within one of the features. Now, let's say that we have a problem like this. On the x-axis, we have one feature. On the y-axis, we have another feature. And then how many groups do we have? Four. It's good that you can separate colors. And let's work on these colors. What is this?
Red.
What is this?
Lavender.
What is this?
Mustard.
Light olive.
That's a
And
color.
that is a
Like
color.
olive.
I would call it beige, but
How was
I
that
call it throw up
beige?
green.
That's not beige.
light brown, I don't know.
There's so much.
Cream.
Green is the dominant color, but it's closer to olive and it's a bit faded out, therefore light olive.
Are you see these as green?
Those are green.
Yes, that
Yeah,
looks
it is
like kind
green.
of like a throw up green to me.
They're green on my screen.
Like I don't know, like baby food green.
Hey, baby food green. That's a
Mustard
perfect
color, yes. I would go with mustard.
Oh, that is so far from mustard to me.
Mustard?
Yeah, that's like the baby food you from like
Maybe
Gerber
like
Life or some shit.
expired mustard. Yeah, I mean, like 3-year-old expired mustard.
Caden, Jalissa, you are using very different classifiers for color.
That is mustard.
That is yellow.
That is mustard.
That is mustard.
That
I
is
agree.
mustard.
That is definitely mustard.
It's also
I don't know
yellow.
what type of mustard y'all are eating that's green.
Yeah, if you're eating green mustard is a problem.
You need
Okay.
to throw away your mustard.
What color is this one?
Saturated teal.
Fine.
Shall we just call it blue?
Yeah, okay, it's blue.
Okay. Now, let's say that we want to use the decision tree algorithm to come up with a good classification for these points. A simple decision tree built on this data will iteratively split the data along one or other axis. These splits along the axis will be basically those questions that we talked about earlier. Let's have a look at this. The first line that we are going to draw is going to split our y-axis into two areas. Everything on top and everything below. Would you say that with this color, I'm capturing one of my groups pretty well? Okay, so I'm going to keep that. And in my next step, where I have to start splitting on the other axis, I will not cut this area anymore because all I have in it is in one color. So next step, I will do a split on my x-axis and go up until my previous split. Now, are you happy with what I have on this side?
Yes.
Yes, yeah.
It's not terrible, but you see some misclassifications, right? Some purples, some yellows, they're not supposed to be here. But in these areas, we are happy. Now,
Yes.
another split, this one should be on which axis?
X.
No, this one was on X. So the next one should again be on Y.
Yeah.
So this time I'm going to make this a split to separate blue and purple in this area. And this a split to keep the greens below. Now, how do you feel about this area right now?
Perfect.
Perfect. Everything in it is blue.
Close to perfect.
I think there is one misclassification maybe here, but it's okay. How do you feel about this area?
Close to perfect too.
Mhm.
Pretty good.
What about this one?
That's horrible.
That's horrible. You have basically very similar shares of all classes in it. And that is not good. So on our next step, we are going to split that area further. Okay? Notice that after the first split, every point in the upper branch remains unchanged, so there is no need to further subdivide this branch. Except for nodes that contains all of one color at each level, every region is again split along one of the two features. So we will end up with something like this. Now, tell me a few of the good things that you see with this classification and a few of the bad things that you see with this classification.
All right, our phlegm color, it's pretty good. It's getting most of it down there. Our bottom right saturated teal looks great. Our top red of a bit of a washed blood, that looks pretty good. And then on the far right middle, our periwinkle lavender looks also pretty good. But in the direct middle, we start getting some noise.
Okay. Anyone else?
I mean, he said it.
So in plots like this, whenever you see weird small boxes like this, what does it mean?
Means it has noisy data.
And?
It's overtrained.
It's overfitting. Yes. Who said that? That was brilliant. So, this is one of the common issues with decision trees. Have a look at this one. What do you think about this?
I like it more.
The
do you
sort
see...
of like,
go on.
Sort of like the logic behind it is very apparent and it's nice to look at, but
exactly.
Yeah.
I don't
So,
like the purple column going down there though.
This one?
Yeah, I don't like it.
This is kind of weird. So, first of all, about the point that Sarah said, yes, decision trees are transparent and easy to communicate and easy to understand. That is one of their benefits and one of the reasons for their popularity. But when you look at this, do you also see signs of overfitting?
yeah, stuff like the purple column going all the way down.
Weirdly shaped tiny boxes, that usually is an indication of overfitting. Notice that as the depth increases, we tend to get very strangely shaped classification regions. For example, at a depth of 5, there is a tall and skinny purple region between the yellow and blue regions. I'm not sure which one I was talking about. I think it should have been green and blue, whatever. It's clear that this is less of the result of the true intrinsic data distribution and more a result of the particular sampling or noise properties of the data. That is, this decision tree, even at only 5 levels, is clearly overfitting our data. Such overfitting turns out to be a general property of decision trees. It is very easy to go too deep in the tree, and thus to fit details of the particular data rather than the overall properties of the distributions. Another way to see this overfitting is to look at models trained on different subsets of the data. For example, in this figure, we trained 2 different trees, each on half of the original data. So similar to training testing that we did before, let's assume that I broke my original data set into halves and I applied one tree on the first half and another tree on the second half. And that's what I get. So what is similar between the results? Are you waiting for me? Okay, go on.
Between the 2 trees on that we see right now?
Yes. Between these 2 figures, what is similar?
The way the yellow is set up.
Okay, so in both of them, if you are in the upper areas, you are in the yellow region or yellow zone. Yes. What else?
Our drab navy doesn't look so bad. It looks pretty similar too.
So if you are in bottom right, you will be in the same zone. What about bottom left?
Well,
similar. What if you were in the right eastern side?
I mean, just that right portion looks pretty close, but the middle and bottom middle don't.
Okay. What about the middle?
Yeah, I don't like it.
They are not similar, are they? So it is clear that in some places, the two trees produce consistent results, for example, in the four corners, while in other places, the two trees give very different classifications. For example, the regions between any two clusters or in the middle. The key observation is that the inconsistencies tend to happen where the classification is less certain. Thus, by using information from both of these trees, we might come up with a better result. So, if you were to make a decision about this data set, would you have preferred to look only at this or looking at both of them? That was a question.
Can you repeat that question, please?
If you are the person responsible to make a call based on the results of these classification models, would you be more confident? Would you feel better to only look at one of them or to look at the results of both of them and then make a decision?
I would say look at both of them, because when we do modeling, you want to look at more than just one.
Okay, that's one answer. Any other ideas?
I'd rather just use the one on the right.
Okay, that is another answer. Come on, share your ideas. Hello.
I mean, the one on the right pretty much does it all better.
So, if I were to give you the chance of looking at 5 other trees, would you take that chance, or would you decide to stick with the figure on the right?
The chance to do 3 trees?
So you would accept the chance to look at more trees?
I mean, yeah, I'd look at it.
Same for Harper?
Yes.
Same for Abby?
Yes.
Same for the rest of the team, or do I have any other ideas coming in? So that is the way that you should be thinking. Looking at more than one tree is beneficial because it allows you to identify the areas and the regions and the zones that you are less confident about and the ones that you are more confident about. So, just as using information from 2 trees improves our results, we might expect that using information from many trees would improve our results even further. And what would we have if we had many trees?
Potentially an overtrained model.
No.
A forest.
They are not working at the same time. They are working in parallel. So when you have many trees, you will have a forest. Thank you. And in fact, if you had many smart trees, you would have Fangorn forest. And if you do not understand that reference, I'm happy that this class is soon to be over. This notion that multiple overfitting estimators, in our case, multiple overfitting trees, can be combined to reduce the effect of this overfitting is what underlies an ensemble method called bagging. You will hear this in the machine learning literature. Bagging makes use of an ensemble, a grab bag perhaps, of parallel estimators, each of which overfits the data and averages the results to find a better classification. So it basically says, on this data, I have 10 trees. I have 10 experts. They think that at this specific point, I will be in this class label. 3 of them say A, 7 of them say B. I'll take an average and say, overall, I would go with B. This is specifically useful when you're dealing with areas of lower confidence in each estimator. An ensemble of randomized decision trees is known as a random forest. And up to this date, after a few years of experience with machine learning algorithms, this is without a doubt the most romantically named algorithm. A random forest. Now, what is a random forest? It is a versatile machine learning method capable of performing both regression and classification tasks. However, it is mostly used for classification. And it undertakes dimensional reduction methods, treats missing values, outlier values, and other essential steps of data exploration, and does a fairly good job. It is very, very common and very useful. It is a type of ensemble learning method where a group of weak models combine to form a powerful model. In random forest, we grow multiple trees to classify a new object based on attributes. Each tree gives a classification, gives a vote, gives a decision. And we say the tree votes for that class. So not only they are smart trees, they do vote. Yay. The forest chooses the classification, having the most votes over all the trees in the forest. And then in case of regression, it takes the average of outputs by different trees. Now, let's have a look at this. In this case, I have 1, 2, 3, 4, 5 trees. When I have a new data, this can be one row of my testing data. Each one of my trees, look at that and gives a vote. Yes, yes, no, yes, yes, yes. So 5 yeses, 1 no's. Our ultimate answer is going to be a yes. This is basically how a random forest works. 5 trees, 500 trees, 5 million trees. The number doesn't matter. Each tree is going to cast a vote based on a new data entry, based on a new testing data. And then the ultimate outcome of the model is going to be defined and determined based on their votes. Do we get this?
I think so.
Awesome. Random forest is like bootstrapping algorithm with decision tree model. Say we have 1,000 observations in the complete population with 10 variables, 10 input features. Random forest tries to build multiple cart models with different samples and different initial variables. For instance, it will take a random sample of 100 observations and 5 randomly chosen initial variables to build a cart model. So this sentence is important because in different trees, you can be using different combinations of your inputs. You may not use all of your inputs for all of your trees. So you're looking at different combinations possible to create from your original data set. It will repeat the process, say 10 times, and then make a final prediction each observation. Final prediction is a function of each prediction. This final prediction can simply be the mean of each prediction. Now, let's work on a rather simplified example. Out of a large population, say the algorithm random forest picks up 10,000 observations with only 1 variable, for simplicity, to build each cart model. In total, we are looking at 5 cart models or 5 trees being built with different variables. In a real-life problem, you will have more number of population samples and different combinations of input variables. The target variable in our example is salary bands. Band 1 are people who make less than 40,000. Band 2, the ones who make between 40,000 and 150,000. Band 3, above 150,000. Now, the following are the outputs of the 5 different trees that we have. Cart 1 is based on age. based on age, we have 5 different groups: below 18, 19 to 27, 28 to 40, 40 to 55, and people who are more than 55 years old. Now, we know the probabilities or the shares of each salary band with respect to each group. So people below 18 years old, 90% of them belong to the band 1, which they make less than 40,000 a year. Band 2 forms 10% of those who are below 18. I would like to meet them. Do you know someone below 18 who can make between 40,000 and 150,000 a year? Probably
Yeah.
these young kids on YouTube and TikTok these days.
Ryan on YouTube.
Who's Ryan? What does he do?
This is like this little 8-year kid who plays.
Is he the
with
one who
toys.
critiques toys?
Yeah. He has
Yeah,
100 million followers.
I think his
insane.
parents should be jailed. Anyway, so age 19 to 27, we have these probabilities and shares for each of our age groups. This is the outcome of our first tree. Our second tree does the same thing based on gender. We know that 70% of males belong to first salary band, 27% of them belong to the second salary band, and 3% of them belong to the third salary band. And we also have the percentage for females. Our third tree is based on education: high school, diploma, bachelor's, master's. You see that there is no PhD in here because we do not exist in real life. So we also have the percentages for those. And it is quite interesting that the share, 11% of people in the third salary band are people with diplomas or high school degrees. And only 3% are people with masters. That gives you the true value of education. So cart 4 is based on residence. So whether they live in cities or non-metropolitan areas. And in cart 5, we have categorized them based on industry. So in finance, in manufacturing, or others. So each one of our trees is looking at one specific input or characteristic. And with respect to that, we get probabilities of belonging to each salary band. So far, so good? Are we following? Sean, it says, I think it basically means whether they live in metropolitan areas or non-metropolitan areas. And based on this, I believe if you are in Dallas area, you will be in metro. If you are in Lubbock, you are in non-metro, but I'm not sure how they are defining it. Okay. Using these 5 cart models, we need to come up with a single set of probabilities to belong to each of the salary classes. For simplicity, we will just take a mean of probabilities in this case. Other than sample mean, we also can consider vote method to come up with the final prediction. I will talk about it in a moment. Now, the new case comes up. You have a person who is 35 years old. He is male. His highest educational qualification is diploma, and he is in the manufacturing industry, and he lives in a metropolitan area. If we know these information about this new case, and it's our goal to be able to classify his salary band. For each of these cart models, following is the distribution across salary band. So he was 35, so he belongs to the age group of 28 to 40. That group, based on this tree, has 70%, 23, 7% chances for each salary band. We will just bring it down and write it here. We will do the same for him being a male. for him having a diploma, for him being in the manufacturing industry, and for him living in a metropolitan area. So these are what we get from our trees. In the last row, when we are going to calculate the final probability, if we follow the mean method, we basically calculate the mean value in each row and come up with the probability that this person with these characteristics belong to the salary band 1, 70%. 24% that he belongs to salary band 2, and 6% that he belongs to salary band 3. How would you deal with this if you were to use the vote method?
The vote method?
The vote method, yes.
What's the vote method?
Good question. Based on the insight from the first tree, the first row in this table, which class has the highest probability?
First.
Salary band 1. So the vote of the first tree is going to be 1. What about the second tree?
It would be vote 2.
Why? 70%, 27%, 3%. Which one is higher?
23. 27. What am I doing?
Compare 70%, 27%, and 3%. Which number is higher?
Oh, you're in another row. Oh, my bad. 70.
70. Okay, so again, the vote for the second tree, as Aaron said, is going to be band 1. What about the third tree? 80%, 14%, 6%. What vote?
80.
80. So again, vote for band 1. The fourth tree.
60.
Again, vote for band 1. Residence, the fifth tree.
70.
So you had 5 trees. You received 5 votes. All 5 votes said band 1. So ultimately, you are going to classify this person as someone with a band 1 salary. Does that make sense?
Yes.
That will be the voting method. Do I have any questions? Okay. The final probability is simply the average of the probability in the same salary band in different cart models. As you can see from this analysis, there is 70% chance of this individual falling in class 1 and around 24% chance of the individual falling in class 2. Now, we are going to work on our familiar example, and we are going to reuse the iris dataset again. So this time we're going to use random forest and see how that works. This is something that I wanted to show you. This pair plot is a very cool plot that you can use to explore a data set. And first, let's have a look at this. Let me zoom out. Okay, now I think you can see it more completely. What does this tell you?
Where the classes range.
What else? Let me ask you a question. If you were to choose 2 variables only for classification of the 3 types of plants, which two would you pick and why?
I'd
Which
probably
two
pick
apps?
like which two flowers?
No, which two inputs?
Oh, okay.
I have one answer from Harper in the chat box.
I'd say petal length and yeah, probably petal width. Yeah.
Okay.
I wouldn't pick sepal length. I wouldn't pick that one, and I definitely wouldn't pick sepal width either, because they're really mashed up together.
Overlapping.
There's not much distinction.
So what was the couple that you chose?
The petal length and width. What Harper?
Petal length and
width.
Petal width.
Yes, sir.
So this one. Okay. Why would you pick this?
Because it's a little bit easier to distinguish each flower than it would be if it was, say, like sepal length, right? Where all of them are kind of together. Like orange is overlapped in almost every single one by the other two. So it's harder to distinguish which one's which.
Okay. And when we look at the couple that you chose, we see that Iris setosa is clearly distinguishable as a separate cluster. We have a slight area of overlap between Virginica and Versicolor in this area, but it's definitely way better than what we see here, for example. So this is an extremely useful plot when you want to explore how informative your inputs can be as couples in classification. And looking at these distributions, the more overlap they are, the noisier your data will be to classify. So you want them to be as easily separable as possible. Okay? Clear? Now, let us move on. I am going to use all of my inputs. I'm naming them X. My Y is going to be named Y for my targets. And then I'm going with a 25%, 75% separation of testing and training. And I am using the random forest classifier function. I'm setting a number of estimators. And I'm going with this random state. What are they doing? N estimators is basically the number of trees that you want to grow. You can go way higher, you can go way lower. And then random state 1, 2, 3, 4, 5, 6 is basically making my results reproducible, because there is a random element to random forest, of course. If you set your random state to a specific number, every time that you run it, you will get the same results. That is necessary if you want to make your results reproducible for like research projects and stuff. I will fit my model on my training X and Y's, and then I will apply it on my X for the testing period. And I get this as my confusion matrix and the result. Do I have a volunteer who wants to tell me what that means?
What this means is it's pretty good. 40, and then you got 40 correct, you got 31 correct, and you got 36 correct.
So for the first plant type, I had 40 and I captured all of it correctly. For the second one, I had 36 cases and I only captured 31 of those, so 5 misclassifications. And for the third class, I had 37 cases and I got 36 of them correctly, so 1 misclassification. So if you want to compare this with the support vector machine, which one would you pick?
The last one.
Why?
Doesn't it have only one error?
So you would pick support vector machines?
Yes.
Okay, thank you. Yes. And if you look at the precision and recall and F1 scores, you will also see that it is not doing bad, but it's not as well as the support vector machine. Okay, pros and cons associated with random forest. This algorithm can solve both types of problems. It is effective in high dimensional spaces. One of the most essential benefits of random forest is the power to handle large data sets. If you notice, this is one of the shortcomings of support vector machines. It has an effective method for estimating missing data and maintains accuracy when a large proportion of the data are missing. It has methods for balancing errors in data sets where classes are imbalanced. And then it is a non-parametric model, which is extremely flexible. So you can use it on a variety of different data sets. On the cons, it surely does a good job at classification, but not as good for regression problems, as it does not give continuous output. Random forest can feel like a black box approach for statistical modelers. By black box, we mean we don't really know what is happening inside it because of the randomized nature of it. You have very little control on what the model does. You can, at best, try different parameters and random seeds. Okay, final remarks. We talked about 3 of the most important and widely used machine learning algorithms in this lab: support vector machines, cart models, and random forests. Support vector machines provide high flexibility in converting complicated, non-linearly separable data into linearly separable data, which is ideal for us. But it does not work well with larger data sets. A random forest is an efficient algorithm for addressing the overfitting issues of cart models, but fails to provide satisfactory regression performance in predicting beyond the range of the training data. The list of readings and videos are a little more extensive for this one because we covered 3 important topics. As the question, I asked, who would you trust, a tree or a machine? What are some advantages and disadvantages the random forest algorithm has against the support vector machine? And with that, if you have no questions for me, I'm going to officially end our last laboratory session together. And just one last meme for you. And that's it for me. So due to demands, I am going to bring up the puppy in a moment.
Dog acquired.
Okay. I'm gonna wait for Farhang to get back in case there was something else he intended to talk about. He's now soothing Kate the dog, who's acting very cat-like. So
hello, everyone.
You're done, right?
Yes, yes.
Okay, very good. So we will see you all on Tuesday. Again, be prepared to provide a very short progress report on your semester project. The first team is Cade's team, and as the rest of you all work it out, you can feel free to email us and tell us if you want to go second or third or so on. On Tuesday, we will arbitrarily pick teams after the first one. So be prepared. Have a great weekend. Do we need to make a presentation or is it all verbal? Well, hopefully you'll use words. No, you don't need to spend a lot of time preparing a PowerPoint or anything like that. If you want to, that's cool. And the typed report, we don't need it tonight. It's whenever it is on the Blackboard. I think it's set for May 10th or 11th. So you have plenty of time to complete it if you've already started. If you haven't started, you're all screwed.
I think he was asking about the interim report. Yeah.
Oh, that is due end of this week. That's right. Let's check what I'm looking at my Blackboard right now. Okay, project, interim report. Interim report is due Friday, April 30th at midnight. And Friday, April 30th is Monday, I think. No, Friday.
That's for the effort sheet, or
Friday, April 30th is the interim report. There's also an effort sheet due on Friday, April 30th. So you have two things that are due tomorrow at midnight. Effort and the interim report. Any other questions before I terminate this call and upload my last video of the semester? Second to last.
And just like that, she's basically going to sleep.
Okay, everyone, well, have a great weekend. It's been fun. We'll also have another surprise for you on Tuesday. We're going to post a survey on the Blackboard, and that is separate from the one that the university has you do, where you tell them how good the teachers are and what a waste of money this class was and things like that. So you need to do that one because they get all cranky about it. At least they don't involve us anymore. But we have our own, and for what it's worth, from last semester's responses, we actually modified the class slightly, hopefully for the better. But we will only know after we get your responses. And I'll leave it up to Farang to activate that. It's still there on the Blackboard because he actually knows how to do that stuff. And those are no pressure on those. They're anonymized too. We don't actually know who says what. So you can get vicious if you need to. We won't know who's done it. All right. Goodbye, everybody. Have a great weekend.
Take care. Be safe.
Bye.
Bye.
Bye.